So my name is Andres González Quiros. I am a hydrogeologist with BGS, and with my colleague David Boon, we will present some of the initial insights of the hydrogeological and the thermal characterization of the UK Geos in Glasgow. So for those of you not familiar with the observatory in Glasgow, this is one of the two geoenergy observatories in the UK to study new energy technologies, geothermal energy, heat storage. And this one is located in Glasgow to study mine water energy, and is in an area typical of many former coalfield communities and with urban regeneration. And it's a research site typical of a small mine water heating cooling scheme. So it's not providing heat to any user, so it's mainly to do research and to test new monitoring sensing techniques, and open for the research community and the industry to develop these activities. So some of the key things about the observatory. The observatory is, we have 12 boreholes. 5 of them are drilled into the mine workings, and other are environmental monitoring boreholes to control different things like groundwater levels, temperature, etc. And we are carrying out continuous environmental monitoring baseline to control different things about the use of the geothermal scheme, such as surface water, groundwater sampling, doing test analysis, chemistry, soil chemistry, gas, etc. And all data is open data, and you can go into this website to download data, the information about the geological, the details of the geological settings, the models, data packs, the details of the drilling, the boreholes, etc. So it's more of the detail and the timeline of the development of the project. So the project started in 2018 with the drilling of the boreholes. Since then, there's been environmental monitoring. In 2020, there was the first hydrogeological testing with a pumping test that I'll show later. And the site is open now for researchers, so you are free to contact and come to use the observatory to do research using the facilities we have there. So this is a schematic figure of the observatory showing 9 of the boreholes. 2 of the boreholes are drilled into the. Sorry, let me move to the pointer. Are drilled in the Glasgow main coal seam. There is about 90 meters depth. There is one deep monitoring borehole with electrical resistivity, DTS. And we have 3 boreholes drilled into the Glasgow upper, about 45 meters depth, and other environmental monitoring boreholes in the superficial deposits and in the bedrock. 2 of the boreholes are ready for water abstraction, one from the Glasgow main, one for the Glasgow upper, with flow rates between 3 and 12 liters per second. And this is all connected to a heat center with a heat pump and chiller of 200 kilowatts. And there is possibility for reinjection both in the Glasgow upper and in the Glasgow main. So we can use different combinations of abstraction, reinjection, both in the same coal seam or in the different levels. So I'll show now some of the initial hydrogeological characterization results we have from this environmental monitoring. Here you have a conceptual hydrogeological model showing the key elements of the site. So in terms of the hydrogeology, we can differentiate a superficial aquifer that is quite connected with the River Clyde. Then we have the bedrock aquifer, the Carboniferous aquifer, mainly sandstone, mudstones. It is quite fractured in some areas. We have the Glasgow upper, where some of the mine working boreholes are drilled and screened into this interval, and the Glasgow main, that is the deeper drill mine workings. There are other mine workings in the area. For example, we have the Glasgow coal that is about 70 meters depth, and other mine workings that are deeper than these mine workings in this area. So we are interested in the connectivity of this system, both the intra-mine connectivity, the connectivity in the same coal seam, and the connectivity between the different aquifers, the different reservoirs, and with the River Clyde and the superficial aquifers. So first, I show here some of the groundwater level monitoring of the different boreholes, you can see here that the Glasgow main, which is the deeper mine workings, shows the highest groundwater level, and slightly lower is the Glasgow upper and the bedrock. There is good connectivity shown between these two areas if we look at the groundwater level, so they show the same groundwater levels and the same groundwater level responses. And then we have the levels of the superficial deposits. This meaning that we have higher groundwater levels in the deeper mine workings than in the superficial deposit. So if we think about the hydraulic gradient in the area, it is an upwards hydraulic gradient. And also if we look at the different levels, this would show that the connectivity is very limited, especially between the superficial deposits and the mine workings. This is really important, especially if we are working with a geothermal installation and we can have any impacts in the superficial aquifers that are used for drinking or with the River Clyde, for example. Here you can see some of the well testing to characterize the Inter-Aquifer reservoir. So the responses are really fast, and the drawdown are not very high. Even with 20 liters per second, you see the highest drawdown in two of the boreholes, 01 and 07 is between 1.5 and 2 meters drawdown with 20 liters per second. And the response in the other mine working boreholes in blue and the bedrock in orange is quite fast, and the drawdown is not really high. However, for the other borehole in the mine workings, the GGO4 that is drilled into the mine, into the coal pillar, the yield was very low and the drawdown was very high. With 15 liters per second, it was a drawdown in this borehole of 18 meters. So we can see that first, the connectivity is really high in terms of pressure. However, there are different areas and different transmissivities and different responses in the three boreholes in the same mine working. So this is important to characterize the connectivity and the long-term effects in the geothermal scheme. Something also that is important to have in mind is that a fast pressure response is not related with a fast displacement of groundwater and also a fast displacement of the thermal front. So the thermal responses in these systems, because of the very high transmissivity and the very low compressibility of water in open voids, means that the pressure front travels really fast, hundreds of meters per second. However, the displacement of groundwater, which is the main driver of heat transfer, is so much more slower and is proportional to the flow rate and the volume. So you can see here, for example, some examples of the different distances and transfer times. While for the pressure front, after 1 day for this injection is more than 8 kilometers, the hydraulic radius, which is the travel time of this injection, is only 25 meters. So this is related with the flow rate, with injection flow rate. So it's different time scales, different times and spatial scales. So this is really important. And of course, we are not in a perfect homogeneous aquifer. We have a very complex and heterogeneous system. First, we know that the processes in these different settings are really complex. They are coupled, and they range from open voids, so flow in open voids, to flow in the Gulf, flow in the backfill areas, and also flow in fracture domains. So we have a combination of conduits, fractures, porous media flow, very high transmissivities, very low transmissivities. So this is really complex, even with very simple geometries to mimic this process, to analyze these processes. And also we have to take into account that this is also something that we have to think when we start analyzing these systems is what's the present conditions of the mine? What's the reliability of the previous information we have? Can we characterize the system using mine plans 100 years ago? So in reality, what we think to know is, okay, we can use models, but we have to ask one question: is it realistic to make decisions using models with this very high uncertainty in the geometry, in the properties, in the processes? we need to understand better all these different aspects of the groundwater system. And of course, these are uncertain, but are not completely unknown. So we have these all mine working plans. We have some uncertainty, but we have to reduce this uncertainty. And the different systems and the different schemes at different sites will show different characteristics. We have seen the Spanish mines, for example, that closed 10 years ago, and we have these Scottish mines that closed 100 years ago. We have uncertain properties. We're still not sure about the permeability of the Gulf, for example, or the porosity of the backfill areas. So we need to characterize this system. Also, we need to understand better the processes, the flow and heat transfer in these different settings, and the transfer between a void, for example, and the bedrock, and or the void and a coal pillar. So what we really know is to increase our knowledge and to increase the data we have, using the opportunities we have to reduce this uncertainty. So through research and experience, we can use the Geoenergy Observatory, we can use the Living Lab from the Coal Authority, of course. We have commercial schemes to start learning and improving our knowledge about these systems. And I like to end with some reflections about how to do the modeling or to think about the characterization of these systems. And sometimes we have these nice mine working plans, or we can digitize these mining plans, but we really don't know what is happening down there. We know from drilling experience, for example, that we're missing targets. We find things that we did not expect. So is it worth it to spend hours building a model with a geometry that looks like the mining plans if we know that the uncertainty is really huge? What's the impact of that in the characterization? What's the impact in the modeling? So something that we have to take into account is that one single strategy does not fit all. The models for the Asturian mines, for example, for the Spanish mine, or for the German mines, or for different mines in the UK, the Scottish mines or the mines in the Northeast, might be different. And how we develop these models, or how we understand the different processes in these mines, we can do different, or we can use different strategies. The second thing is this saying, if it looks like a duck, might be a duck. Well, if it looks like a perfect mine with very nice colors, it doesn't necessarily mean that you'll have these results. We need more data. We're still learning about the processes. We need more data and more knowledge about what is happening there. And that goes to my third point, that is the data, what type of data we need and how we should collect this data. What are the best strategies to characterize and to monitor the commercial scheme, and what is realistic in terms of time and in terms of costs for the commercial schemes. And about data, I pass on to Dave.
Yeah, so I'm aware we've got about 7 minutes left. I think we had a 20-minute slot, so I will try and sort of get through this. So thank you very much. So yes, as Andreas has pointed out, we can build fantastic all singing, all dancing models, but they need to be grounded in reality, and that means collecting good data. But we have to also ask ourselves, what's the level of data that's kind of economic and practical for operational schemes to collect? Of course, with a research park like UK Geo's Glasgow, we have the opportunity to collect very high fidelity data using a very well instrumented system. And I think that's one of the powers, the benefits of having a facility like this. And the other thing is there's no customers using this for operational, so you can turn it on and off as you like. You can heat it up and cool it down as you like without annoying any homeowners. So it's a place to come and play and do process research and also engineering research. So I just wanted to share a couple of sort of the early data sets that we're collecting to show the types of data that you can collect from these sorts of monitoring systems that we've got. So the slide here shows top left one of the wellheads that Kenza Engineering have constructed, our principal contractor, and we designed the system with Casper, who may be on the call, to make sure that we had a lot of different temperature and pressure monitoring points right across the ground source heat pump system, or the ground mine water heat pump system. So you can measure each wellhead flow temperatures and pressures, as well as on the different parts of the heat exchangers and the heat pump chiller themselves. So you can really get an in-depth understanding of if there's heat losses in the system, and kind of what's happening at each part of the system, if you like. So to augment that, we've got control panels where you can get real-time data and set your experiments running. So you're able to kind of control and program experiments that you want to run and get real-time kind of feedback from the system. A lot of that data is going to be, and some of it already is, put onto a live kind of data viewer, which is an online web viewer that you can see on the top right there, an example. And we've even got sort of live seismic monitoring data going into that. So you can actually explore and interrogate data using a variety of tools that have been developed for researchers and for the public to be able to go and have a look. Going back to Finlay's talk and the importance of kind of informing the public and keeping them in the conversation and being very open about what's going on. If you could flick to the next slide, please. Yes, I want to share some results from the fiber optics. So in these wells, we had the opportunity to install fiber optic cables, which allow you to, because of the properties of glass that are, so down the wells, we actually installed fiber optic cables outside on the outsides of the PVC casings. We use PVC casings because if you use steel casings, you can get heat transfer up the casing. So we can get a very, by putting it on the outside of the casing, well, it's technically difficult, but we have the help of Silixa, who are our DTS experts. You can actually try and measure the formation temperature rather than kind of what's going on in the well column itself. So some examples of some data here from, so all the wells have fiber optic cables in them, and we're constantly monitoring them on site using interrogators. So some examples, I wanted to show 2 slides on this. So the first, to give you an example of the kind of temperature responses we can see with this type of fiber optic technology. So the first one here is showing an example of a run period in November last year where we're extracting water from one of the abstraction wells, which is well 5, which is about 135 meters-ish away from one of the injection wells. These are both 2 80-meter wells, so they're the 2 kind of wells that are screened across the deeper coal mine seam called the Glasgow main. So you're abstracting from one deep coal mine seam and injecting into the same seam, like 100 meters away. And what we can see is when we abstract, we didn't really see any temperature change using the DTS cables in the well. And when we inject, we do see a temperature shift in our wells. And you can see the plot on the kind of bottom right-hand side plots on the 23rd of November when this commissioning was being doing. So at that point, we were actually injecting sort of 35-degree water or between 10 and 13 liters per second into that injection well as part of the commissioning testing for the site. They then switched to cooling mode on the heat pump chiller, so you can add heat or take heat out of these mine shafts as you like, using basically a large sort of air source heat pump chiller that's at surface. And then you can see in the data, so we went for an initial kind of hot warm spike into a cold injection period. And from this, I guess some of the detail I want to pick out from that was that you can see the DTS data shows very nicely the distributed temperature measurements down the hole, which are at every 0.25 meters where you have a temperature measurement essentially. And that's one of the massive advantages of using fiber optic cables. You get continuous temperature profiles in a well, and you can start to see sort of individual bands of rock, if you like, and the kind of response that they have in terms of thermal properties and flow properties. And it's interesting at the bottom of the well there, which is the bit that's screened off, the cold water that was injected basically warms up much quicker than above. And that's probably because the mine water's down there is the bit of the system that's flowing, if you like. So the coolth that was put in there, basically started getting replaced by the formation water much quicker than the well above it because it's unscreened. Can you just flip to the next one, please? And it's an example of zooming in on that special day of the 21st of November when we did this heat injection test. So I'm showing on the left is the same slide example from that injection well where you can see a blue period. So we've got time and depth, and the color is showing you the temperature of the water in the well or in the back of the casing. The water table is quite near surface. It's 3 meters below surface, so it's basically a saturated, carboniferous sequence. And you can see here we had injection for kind of 20 minutes, which warmed up the well, and then we had a period of cooling, which cooled down the well. And it's interesting to see on these well pairs. So what was the impact on an adjacent well, like 10 meters away? So 10 meters away from this injection well, we've got an observation well in one of the higher coal measures. So one of the seams at about 50 meters below ground level, rather than the one so we're injecting into the one about 80 meters below ground level. And then we're looking now on the monitoring well at this higher system. And essentially what we're seeing is there was no thermal impact on that higher system, which, you could say, well, suggests there isn't sort of hydraulic connection between the lower seam and the higher seam, as was kind of also seen in the pump test that Andreas showed earlier. But I think what we need to say, the caveat on that is, well, we only ran the test for a couple of hours, so you wouldn't expect to kind of saturate the system or any fractures in the system at that time. So you'd need to run it for longer to really see if there was a connection. But it illustrates the kind of monitoring capability that we've got on the and the kind of data you can collect to help validate thermal breakthrough models and benchmarking, kind of what different monitoring approaches could give you. If you'd like to just go on to the next slide, please. I guess, sorry, I realize the time's going over a bit, so I'll try and get through this. But we also had the opportunity with Glasgow. We did core one of the boreholes, which allowed us to, take intact rock material from the subsurface for the purposes of analysis. So that core has been scanned in our core scanners at BGS in Nottingham, and all that data is actually on our website now, so you can go and look at it. Thanks, Gareth. Okay. And so, yeah, a lot of this data is going out into the open, so researchers and others can benefit from it. So within that core scanning, I'm talking about things like gamma, resistivity, density measurements. Down solid pieces of the core are scanned, like meter lengths of solid core are scanned first. We've got CT scans, so you can see fractures and different features within the rock. And then the cores are slabbed, and we've undertaken XRD and XRF sort of scanning, so you can get geochemical data, very rich geochemical data sets right through that continuous coal measure sequence. We're also interested in thermal properties, because thermal properties, as Andreas has alluded to, are very important for controlling heat flow in porous and non-porous media. So we as a mini project, we applied to the UK Geos team to have access to some of the core, which anyone can do, and several other universities already done this as well. And we managed to we took subsamples from 20 subsamples from representative lithologies along that core, so coal, mudstone, siltstone, sandstone, and limestone lithologies, as being the kind of typical lithologies you would find in that kind of geology. And then we took them into our lab and tested the thermal properties in a saturated and dry condition using a modified transient plane source method. We also determined bulk and dry density and effective porosity. And we're also undertaking currently mineralogical and petrological analysis, like thin sections of those subsamples and XRD to sort of supplement the core scanning data. So we'll have start to build a better indication of how the physical properties relate to the microscale properties and the sort of sedimentary processes that have set the rocks in the microstructure that they've ended up with. Could you go to the next slide, please? So I just wanted to share some early results. So in the literature, there's not much data for UK carboniferous rocks for thermal conductivity. I think there's 2 boreholes in Scotland and the Harewood borehole in Leeds. And basically the data on those is, that's not much data really in the big scheme of things. So we need to improve our kind of data bank, if you like, of thermal conductivity properties for UK rocks, all UK rocks actually, but including these carboniferous rocks, if we want to be able to model and predict how heat might flow and be stored in these formations under the ground. So what we observed was kind of expected, but kind of interested. So I know tables are a bit heavy when you're looking at on a slide, but I guess I want to draw your attention to the second column, the thermal conductivity saturated. If you can just wave that, Andreas. Essentially, what comes out is that the Carboniferous rocks have a very wide thermal conductivity range from 0.4 to 3.9, which is, you know, an order of magnitude of like 3 times basically. And what it means is those properties are very variable through the beds, depending on what type of lithology you've got. And the lowest thermal conductivity values are the coals, which typically known to, which are very thermally low thermal conductivity. In fact, coals have a lower thermal conductivity than water, so they would actually be an insulator, a natural insulator, whereas rocks like sandstones and siltstones might have much higher conductivities, and they'd be more like sort of concrete. And you know, they tend to sort of help ease the flow of heat, and might not be a good thing if you want to store heat, because it might leak through those kind of zones. So that's kind of interesting. And then we found what was surprising was the mudstone, siltstone, coal values we measured were slightly higher than the literature values, which is kind of interesting. But we need to collect more data. And we've got a new data set of limestone for the first time, I think, with the limestones that you rarely get some limestones in these rocks. So we've got a new data point there. So we're going to keep building that up, and I hope other projects will have the opportunity to start to analyze some of the materials that they're getting out of the ground. Okay, next slide, please. Can we just snip to the last slide, I think? Yeah, so sorry, just the one before that. Go back one. This is a photo of the heat pump chiller, the big white unit there that Kenza designed and installed, and a heat center, which is on one of the sites in Glasgow. So you can come and visit this site and learn all about it if you like. We're having an open day, I think in the month's time, on the 19th of May, I think. But there'll be further open days for people to come and explore, and a kind of mechanical diagram to show there. Essentially, this place is amazing that you can extract heat and inject heat into the different mine water seams as you like. There's 3 different types of heat exchanger. It's all very well insulated. So it's a place to kind of come and learn and test the kit itself, as well as run. I think there's at least 250 different combinations of experiment that you could run, we worked out on this site. So yeah, it's really exciting, and we really do want people to come and use it. So get in touch. And if you can just go to the last slide now. Yeah, so in summary, the facility that was funded by Bayes and built by BGS with our subcontracting teams is a unique and flexible research infrastructure to support development of mine water geothermal in the UK and elsewhere. And we've provided, hopefully we've shared with you, and you can take away some initial understanding of kind of what we've been doing to look at the hydraulic connectivity and transmissivity of the main units with short-term tests. There's still lots to do to look at the kind of longer-term heat flow dynamics. We've got research grade equipment in place, and you've seen some examples of what that can kind of do and what the data looks like to measure pressure, temperature, chemistry in a real-world setting. We need to know more about thermal properties and hydraulic and geochemical properties and microbiological properties across the scales in these rock masses in order to design and maintain good systems. And I mean, we're delighted. The geothermal infrastructure has just been handed over from our construction team at Kenza to BGS, and we're now working on various example data sets and case studies to support commercial users who might want to come and do experiments, which might even include, you know, using solar collectors to put heat in the ground, and help you with grant writing and gain initial insights for future users. And we do work with the Coal Authority to see where we can cross over and learn from each other as well with the Living Lab. So the site's open for use. There is the UK Geos inquiries at bgs.ac.uk email address if you want to get in touch.